Hello, I'm Dae-Young. In this presentation, I'll share our recent work on image outpainting. As you can see in the video, outpainting is a type of image editing. We start with an original input image. Around it, there are unknown outer regions. The goal is to infer those missing parts and generate what could exist beyond the borders. In the case of inpainting, it is relatively easy to fill the inside by referencing the surrounding pixels that enclose the unknown region. However, outpainting is more challenging because the unknown region is not fully enclosed. In prior work, outpainting has been studied mostly in the single-shot manner, which is convenient for training and implementation. In single-shot outpainting, the reference and the unknown region are placed together in the generation window and expanded at once. This has the advantage that the task finishes in one pass and all context of the input image can be considered. However, when the resolution of the output becomes large, it requires high video memory, and the extended area is prone to blur and loose details. The images on the right visualize the blur level of the images on the left. Brighter regions indicate stronger blur. By contrast, the patchwise outpainting adopted in this paper divides the picture and expands it little by little, so it requires less video memory. Naturally, because the model performs generation for each window, fine details are easier to preserve. However, since the task must proceed over many patches, it takes a longer processing time, and it is difficult to consider the long-range context. At times, sky-like water or land-like sky makes rivers in the sky or seas on the ground. Thus, careful placement of the generation window is essential for patchwise outpainting. Our patchwise outpainting proceeds as follows. First, we choose a local window to be directly expanded and a global window to supply context. From these, we can obtain a painting mask and a location mask. Second, we feed all of these jointly into the model to produce the expanded local window and paste it back into the entire image. By repeating the generation multiple times, we obtain the final result. Here, tau denotes the number of expansion attempts. Initially, we adopted ControlNet as a baseline design. This choice is convenient because we only need to adjust the number of input channels in the hint encoder. In addition, ControlNet benefits from stable training because the weights in control encoder are copied from the original. ControlNet works by adding the silhouette of information from the reference branch to the main branch. It is useful for fixing shape or geometry, but not ideal for automatically inferring context-appropriate objects or backgrounds. Therefore, we designed a Diffusion module that manipulates the main encoder. This is a detailed illustration of the Diffusion module. The key principle is to use attention to integrate the input, the hint, and the corresponding masks. In advance, we extracted a location mask to explicitly indicate to the model where the expansion should occur. Both ControlNet and the Diffusion module are easy to adopt because they follow the loss function of the widely used diffusion architectures. To simulate cases in which the model considers the global context under arbitrary conditions, we propose a new data augmentation scheme. The augmentation code is publicly available and includes logic to generate images corresponding to an arbitrary number of tau. We consider two scenarios to evaluate our painting performance. First, we remove an interior region of the original image and regenerate it as shown on the left. In this case, ground truth is available, so we can use the corresponding evaluation matrix. Also, we keep the original area and expand the exterior region as shown on the right. This scenario is also included in our experiments. For the interior removal and regeneration case, we measure FID, patch FID, clip text score, and clip aesthetic score. Notably, our approach shows a strong advantage in patch FID, which reflects local image quality. For the exterior region expansion case, no ground truth is available. Therefore, we rely on the clip aesthetic score and a blurriness metric. Our patchwise outpainting with a global consideration keeps plausible global context comparable to single-shot method while making better local detail. We also provide blurriness map in the paper. Especially with Firefly, the central input area and the exterior show such a strong intensity disparity that a dark, box-like artifact emerges. In addition, we compare our method with other reference-based painting approaches to clarify that our design intent is fundamentally different. We adopt two promising reference-based methods, paint by example and real fill. Prior reference-based methods inject explicit cues from the reference into the output. In contrast, our methods focus on inferring objects and backgrounds that are plausible given the global composition, even when no explicit corresponding cue is available. Therefore, when patchwise outpainting is processed with our methods, artifacts such as duplication are mitigated. Moreover, unlike real fill, our approach does not require online learning like RORA. A single offline training is sufficient. For natural scenes like mountains or lake, composition matters less, and repetitive patterns like trees help reduce the drawbacks. By contrast, in indoor scenes, the weaknesses of existing methods are pronouncing. In addition, on our project page, we present plug-and-play examples. We first train the Fusion module on vanilla stable diffusion in painting model, then attach the trained Fusion module to other realistic checkpoints without additional fine-tuning. For near 3K results, please refer to our project page. Thanks for watching and see you at the conference.